Alright, welcome back to the classroom. This is Mr. Wong speaking. We are going through Module 8, Inquiry Question 3, with specific focus on this particular dot point, analyzing the contribution of Schrodinger to the current model of the atom. Now, in this particular inquiry question, we are looking at the quantum model. So we're going to be explaining what this guy here, Edwin Schrodinger, you might also know him as, another analogy of Schrodinger's cat, how he came up with this particular concept of the atom and other kind of imagery that we know of with the quantum version of the atom today. So I want to just quickly show you these two animations here. With the quantum model of the atom, we actually come up with the concept of uncertainty. So we're saying that any measurements we make at a really tiny scale, there's always going to be an intrinsic uncertainty that the behavior of the particles are probabilistic. What that essentially means, if we use the example of light. Now, light at a really small scale, what we find is the more precise you know of the position of the light, the less accurate it is to know about the momentum of the light. So these two diagrams, these two animations that we see here, is a single slit experiment that you can use with any laser. So long as you have a laser and you have sort of tiny gap, you can even do this at home. As you point the laser through this little slit here, okay, you'll see a little beam. That's the diffraction of the laser that you see. Now, if you close that gap off, so let's say you have two books, and you try and close off that gap. Now, to you might think, if I shoot the light through and I have my two books and I'm closing them together, then I'm more likely to be able to predict that the light is just going to go through like so. Okay, so by that I should be more knowledgeable of the position of the light. But what actually happens, as you can see, the momentum of the light sources increases. So the closer I think I know where the position of the light is, it doesn't actually happen. And this is what we mean by an analogy of the Heisenberg's principle. Okay, the probability of where the light is will increase as we believe we know where the position could be. So you can't actually make two definitive measurements at the same time. So how did Schrodinger come up with this idea of uncertainty for the model of the atom? Okay, on the left hand side you'll see Niels Bohr's concept. Now remember, this is also part of early quantum mechanics, this model of quantized energy states, discrete energy levels as well. He came up with the concept that there is no absolute certainty where you know these electrons are. And so he introduced the concept of the electron cloud. Okay, so the electron cloud is a region in the atom where there is a high probability of finding electrons. But that's not to say it's the same as these energy levels. They can be distributed around this entire space. As a matter of fact, this sort of electron cloud will predict roughly 95% of the electrons to be within this area. So that's the idea there. He also introduced subshells. So within Niels Bohr's model, where we had discrete energy levels, inside these energy levels, we also had sub-energy levels or subshells where other electrons can be. There are 4 types of subshells. You have the S, the P, the D, the F. If you did chemistry in year 11, you will have some idea of what these are. It's just the arrangements of where pairs or single electrons are placed in the atom. And they have really interesting shapes, right? So these are all the different types of subshells in the main energy shell that we're talking about here. If we actually look at the periodic table, we'll always talk about shell 1, shell 2, or energy shell 1, shell 2, shell 3. What's actually happening is within each energy level, so energy, or you could think of this as the individual shell, there are many subshells. So in shell number 3, we have the 3s subshell and the 3p subshell. Okay, so the question is, what implications does this have on our understanding of the atom now that we have these little mini subshells? Well, it can actually explain some really important concepts that we said were limiting factors of the Bohr's original model. So we talked about how atomic emission spectra is caused by the shifting of electrons moving from a high energy level to a low energy level. Okay, anything in the visible spectra, we also stated that it was from any number to 2. Okay, now here's the other benefit of this subshell model. Okay, this hyperfine line splitting that we talked about here. So remember when we talked about if we have these lines here, there's going to be splitting or little clusters of other lines next to the main intensity line here. So this is the main spectral lines, but then we had all these little faint little clusters. Now the reason why these clusters existed was because the transitions could be from different subshells. So we could have a transition from level 4 to level 1. Okay, for example here. Now what's actually happening is, instead of having it come from one specific part of level 4 or just from level 4 down like so, it could be from a different region of level 4. So instead of 4F, it may be a transition from 4D. Now not very straight, but you get the idea there. Okay, and so that kind of helps us explain where this hyperfine line splitting occurs. It's actually because in the energy levels there are smaller subshells that are causing this transition to occur as well. Obviously the main favorite one is the one you see there, so that's what we have. Okay, this is actually Schrodinger's equation, so the probability equation to look at what we call the wave function. So it represents the probability of an electron in a given region of the atom. So that's the prediction that he established with his equation there. You can also find it in different models. So the current model that we go with in terms of the electron orbits, we talk about it in terms of the different types of shells, subshells, so S1, S2, S3. We have P2, so all these, and then surrounding the electron there. As you can see, we have the nodes and the antinodes. So again, that's the region where there's no activity. That's staying consistent to what we talked about with standing waves, because we said with waves we have the antinodes and we have the nodes there. So remember, in a standing wave, we draw it out. The antinode is this section here where we have the maxima. So the maxima is obviously the region of space that we have here, and obviously the region where there's no distribution, that's the node. That's what we're seeing here as well, being consistent. Okay, so what was his actual contributions? There's two things. Firstly, the existence of not just orbitals, but as standing waves, they exist in an electron cloud. Okay, so they don't exist in specific orbitals, rather they exist in a specific region in which the electron cloud represents about 90 to 95% of where all the electrons will be in. And we also know that the orbitals can be broken down into subshells, sort of like little mini rows, and that comes in the form of S, P, D, and F. So that is Schrodinger's model of the electron configuration inside the atom, and that's the significance of his contribution there. You might also have heard the concept of Schrodinger's cat. So it's a clever thought experiment in which a cat is placed inside a closed box, and it is placed, and poison is placed inside the box. Now, according to the quantum mechanics of uncertainty, there is a 50% chance that when the flask is broken, the cat could be killed, or it could be alive, or it doesn't break at all, sort of a thing. So Schrodinger argued, until the box is opened to reveal the outcome of the experiment, the cat can be considered simultaneously alive or dead. Okay, how does that apply to quantum mechanics? Well, it shows that in a similar manner with the nature of light or with the nature of electrons, the outcome does not actually exist until an observation has been made. So I could observe the photoelectric effect, or with light, if I just let light be, until I actually observe the photoelectric effect, I won't know if light is behaving like a wave or particle. If I look at an electron and I see diffraction, then I only see one outcome of what it is, the wave outcome. I don't see the particle outcome of it. Okay, so there's no one or the other once you've actually seen the outcome there. So that's the beauty of Schrodinger's cat analogy, is to show that when we talk about quantum mechanics, the behavior of whatever we're trying to observe will not be known. But once we do know the outcome of one, we wouldn't see the outcome of the other one. It's already been set in stone. Okay, so that is a summary of what we've done with Schrodinger's contribution. So he developed a mathematical model, an equation that gives us the probability of the positioning of the electrons. The model was an advanced interpretation of Bohr's interpretation. So instead of the quantized energy states or the specific levels, he used electron clouds. And it gives rise to an observed situation that when applied to large-scale systems, with the box, how we can only observe one thing and not the other. Okay, so that kind of rounds off our explanation of the quantum model of the atom. Hopefully you've enjoyed the learnings of this inquiry question. Once again, you're always welcome back to the classroom to rewatch more videos or learn about new concepts. Anyhow, I'm Mr. Wong, thank you for joining me, and we conclude inquiry 3 of module 8. So we have only 2 more inquiries to go.